plus 1 squared. Right?
And its real part is 1 minus omega square.
And we replaced s by g omega, so we had 1 minus omega squared
Divided by 1 plus.
divided by 1 plus g omega squared. And then we computed the
Whole square.
Whole square.
so we computed the complex part of this. So this will be 1 minus, not the conjugate of this. So this is 1 plus omega squared, the whole thing squared, multiplied by 1 minus g omega. Huh?
Yes.
The whole thing squared.
Whole square.
So when we compute the real part, we had 1 minus omega squared, the whole thing squared, divided by 1 plus omega squared, the whole thing squared. Is it correct?
Yes, sir.
And then we compute the amplitude of s squared plus 1 divided by s plus 1, the whole thing squared. And we find the amplitude is 1 minus omega squared, the whole thing squared, divided by 1 plus omega squared, the whole thing squared twice, huh? So this is to the power 4, I believe. This is the amplitude square. If we take the square root of this, the amplitude, this is the amplitude square. The square root of this will give you 1 minus omega squared divided by 1 plus omega squared, the whole thing squared, which is the amplitude. So this is okay. You are okay with this? So I will be what is the
Fold out the next downside.
Is this correct? So the question is to compare the real part to the amplitude. So we have the real part is equal to 1 minus omega squared divided by 1 minus plus omega squared, which is always positive and equal to 0. It will be equal to 0 at omega equal to 1, right? So the function is like this. When omega starts very small, omega equal to 0, the limit of this is the ratio of the numerator of the denominator. So it will be 1. And then when omega goes to infinity, it's the same thing. You look to the highest amplitude, so 1 over 1 and the highest amplitude here, and then it will go also to 1 again. So this is when omega equal to infinity, and this is when omega close to 0. And then at omega equal to 1, it will be 0. So maybe something like this. I don't know how it is, but maybe something like this. So we are not able to find epsilon such that this real part will be bigger than epsilon. Everybody's okay with this? So there is no threshold here, and they say there is an epsilon. The amplitude, the real part is above this epsilon and above 0. There's none. So I cannot write real part bigger or equal to epsilon strictly to positive. I can write this. So I know that the system is passive, okay, but it's not strictly passive. Strictly passive. Now the other condition that we have to look at is to compare the real part to the amplitude of the system. And they are equal. So I can say that the real part is bigger or equal to epsilon multiplied by the amplitude of s squared plus 1 over s plus 1, the whole thing squared. Right? And this is always positive, of course, based on what we have. What we have found here. I think there is something missing here, no? Is the amplitude correct that we found here?
Last week we had it in square.
You have the whole thing squared, huh?
Yeah.
So I think this is the right one, but it should not be square.
That one, the denominator is squared, not the power of 4.
If we take the amplitude square,
Yes.
this will be to the power 4.
Power
No,
of
it will be power of 2.
Out.
It will be squared.
So the real part and the...
So the amplitude of, if we take the amplitude square, this is this times this, huh? Square, this is the square, the whole thing square. If we take the amplitude square, if we take the square root of the amplitude, then it will be only this to the power 2. So this term is always negative. Not always negative, but we cannot define if this term is positive or not. 1 minus omega squared depends on omega. So if omega is bigger than 1, it becomes negative. Below 1, it's positive. So there is no sign that I can say this is bigger or equal to 0. And so here there is an issue with the amplitude. So now we go back to our definition. How we are going to make the... I usually don't accept this is right. Yeah. So So this is the definition that we have. If we are able to find, not this one, the real part, which is after this one. After and before. So if the real part of g of s is bigger or equal to epsilon, the amplitude is squared. So we need to look at the amplitude squared. This is so it's bigger or equal to the amplitude squared. Then we are able to conclude that the system is output strictly passive. So this is where we are going to look to the amplitude squared here. Of this. Amplitude squared of this. This is the amplitude squared. So as we compare between the real part and what we have here with the amplitude squared.
1. With the square?
So,
With the square?
with the square, amplitude squared. This is our these are our rules, our Bibles, no? Our Quran. لا يمثل طبعا. These are our rules. It says if the real part is bigger or equal to epsilon times the amplitude squared, then you are able to talk about output strictly passive. So we have to compare to this. So when we take the square, this part will be squared, this one will be also squared. So based on this, this is new result. So based on this new result, we are going to conclude that this system here will be multiplied by 1 over 1 plus omega squared on the amplitude. Right? So the more omega goes from 0 up to infinity, the more this value becomes smaller. So we are not able to say that this is bigger than the amplitude. Right? It's always multiplied by a small value. In fact, we are able to say that this is bigger than the amplitude.
Yes,
because we are multiplying by a small value here.
Will be 4, yes.
Yeah. So when epsilon is equal to 1, we are already bigger than the amplitude. So we are able to conclude this part. The output strictly passive.
So the output is strictly passive, right?
Output strictly passive. So this is what we did also with the case, the previous case with this example here. Huh? So it's always to compare with the amplitude squared. Does it make sense? You can do it as a homework later and check the calculations. How it works. I stopped at this level last time when we talked about passivity from energy point of view. And then we are looking to this and we are saying the system has to satisfy this part. In fact, in reality, in general, it has also other part that can go here as part of the state, so as part of the input and the output. But in general, this is how it looks like. So we are talking about this one here. We are saying this will be the supplied energy. So the supply of energy, which is the input multiplied by the output. Input to the system. Huh? So the output of the controller. This one, this here, if you are in a closed loop, is equal to energy stored. So this is the energy stored that we have in the system, plus the energy dissipated. And we have here two terms: energy dissipated at the level of the output, and energy dissipated at the level of the input. So basically what we are saying, if we look to this, we are saying that if there is any energy coming inside the system, either stored or dissipated, it's coming from the input. Okay? So if this term is positive, this term is positive, this term is positive, then there is nothing created inside the system that is contributing to the energy that I'm supplying. And therefore the system is passive. System is passive means the integral from 0 to tu multiplied by y is positive, means that there is nothing coming from outside, or the system is not generating power
Energy.
or energy other than what I'm supplying to the system. This is the passivity here. And when we look to the index of passivity, we are talking about system strictly input passive, strictly output passive, or we can talk about system that is lossless, right? The system that does not lose any energy. Right? Whatever I'm storing is equal to whatever I'm inputting to the system.
Does passive equal stable?
No. Passive may lead to stability, but not a system is stable can be different. Yes.
Every stable system is a passive system or not?
Every
On the other
passive,
side.
Every passive system
every
is
passive
stable.
system is stable,
Okay.
but the system itself does not have to be passive. All right, so if we look to a system with lossless, for example, if we take an example, a small example. If I take, for example, x prime equal to u, and then y is equal to x. So this is my state space. This is my output. What I need to do is to define a storage function. A storage function is a function that is positive. Right? So I will define function b equal to half x squared. This is my storage function. Everybody is okay with this?
Yeah.
So if I take the derivative of v, I will have v prime equal to x prime multiplied by x. And this, according to my definition, is equal to u multiplied by x. But y is equal to x, so I'm able to write this equal to u multiplied by 1. And now I take the integral from 0 to capital T from both sides. And I'm interested only to the last value, this one here. So I will be able to write the integral from 0 to T of u times y deta, right? Integrating from 0 up to T is equal to the integral of v prime from 0 to capital T. So this is v of capital T minus v of 0. Right? So what you see here is that the supplied energy, u times y integrated from 0 to T, is equal only to the stored energy. There is no dissipation. Right? There is no dissipated energy, neither at the level of the input or the level of the output. So what we say about the system is that it's lossless. Whatever we supply, we store.
So what is here capital T on the U of T? So transpose.
This one is the transpose. The one inside is the transpose, and because the formulation is in general, we have many inputs.
So this doesn't exist in reality.
Integrator. Integrator means a tank. and tank with infinite capacity. Whatever you put in the tank is stored in the tank. It does not go up.
It's not possible to realize.
An infinite tank. So, right? But it's an integrator. Every integrator has a limit. So if you want to make an integrator that will have a limit, it means that you put a lead. So when it's full, we stop pouring water. Everybody's okay with this? So this is the last
Is
system.
the storage function? I'm not clear about it. Storage function.
Yes.
V is equal to
X
X
squared.
squared.
Yes.
So how do we relate with this?
This is the storage function. S of t here is the storage function. Here I defined my storage function V as equal to half x squared. V, this is S if you will. Huh? This is S. This is S prime. And this is S of t minus S of 0.
The storage function can be different based on the
Can be
condition.
different. Can be different. You select the storage function. Usually for passivity in particular, the storage function that we select are energy functions.
Energy functions.
Yes. So we go to mechanical system, we have potential energy, kinetic energy, we go to thermodynamics, we go to conservation of mass, conservation of whatever temperature, right? So you put all whatever the conservation equations for systems or the mechanical system, you put potential and kinetic. For the electric system, you put power and whatever energy, U times I and others. So these are the functions that we you select. I wanted to notice here, I did not impose that V prime is negative. Remember, we have seen Lyapunov who said Lyapunov is a positive function, and then if we are able to make the derivative and derivative is negative, then the system is stable. Here I did not impose that derivative is negative.
ST and S0 should be finite.
S of capital T minus S of 0 should be finite, yes. Based on this function, they are finite. Alright, now what will be dissipation at the level of the input? At the level of the output. Let me start with the level of the output. I will start, let me try to put some example here based on electrical system. So if this is my input U, and then I have, for example, a resistance here. I'm going to call this resistance R, and an inductance L, and I have a current here that I'm going to call it X, just to have the same notation. I don't use I as current. So if I would like to write, if my output, in my output I will consider output is equal to the current. Y is equal to X. So Y is equal to X is my current, and then U is my input, is the voltage. So if I write the equation, dynamic equation of this, I will have L multiplied by di dt or L multiplied by X prime. Okay. Is equal to the input U minus R multiplied by the current. Everybody is okay with this? And then I will have here Y equal to X is my my output. So this is my dynamic system. Now again, I would like to show what type of system is this. So I'm going to put storage function. I'm going to select V of X is equal half of L multiplied by the current squared. Half of L multiplied by the current square. If you want, I can define it as S. Everybody is okay with V and S here?
Yeah. So how can we decide this function so that it should be equals to the
Random, yeah.
The only element that can store here is L.
Yes.
So I put L multiplied by X squared, the current square.
Sorry.
Sorry?
X, it's like the states when we design the output here, the Lyapunov. So we took the
It's a
stop.
positive function for me here based on the inductance. I have L multiplied by X prime, so I put L here to make it easy for me to make the calculations. right? But I could have selected half of x squared like before, but I will find some coefficient. So if I take the derivative, v prime of x, it will be equal to x prime, lx prime multiplied by x. Okay? So lx prime multiplied by x means I will have v prime is equal to u multiplied by x minus r multiplied by x squared. You agree with this? Right. Y is still equal to x, so I will have here y equal to x. So this would imply v prime is equal to u multiplied by y minus r multiplied by y squared. And then if I take the integral from both sides, from 0 capital T, so I'll be able to write the integral from 0 up to capital T of u y theta, which is based on our notation is u y bracket, right?
Yeah.
This will be equal to v of capital T minus v of 0, or s of capital T minus s of 0, right? Plus r, the amplitude of y squared. Right? So this is y squared. It's one segment like this.
Output.
This is the output. So r multiplied by the amplitude of y squared. And then when you think about it, if there is any dissipation of energy here, it will happen at the level of R, the resistance. So here I'm losing, we are dissipating energy through R. Everybody is okay with this? So stored energy, normally capacitance, we are ideal capacitance, there is no stored energy. Right?
Yeah, maybe it's on this.
But in normal life there is always some. And then you have the dissipation of energy happens at R, at the level of the earth, which is the current. You agree with this? We can add capacitance and do exactly the same thing. We are going to find similar equations, right? But the capacitance rather than LdIdt, we have to define voltage, and then we have the voltage C multiplied by the derivative of the voltage is the current. Now, if I would like to see what will happen at the level of the output, I think one of you asked about the input last time. So we can imagine, for example, this voltage is basically coming from a source of current, and then we have a resistance here. I'm going to call this R0. So the source of current is my input now. My input U is the source of current, right, that we have inside the system. You agree with this? So how we are going to do this? Let's assume that this current is equal to I, or just not to be confused, let's assume that this current is now my U. It's more confusing, eh? Put current, remove the voltage. So current is my input now. So what will be the equation for this one? So the current is the current that circulates here, right, in this loop. So what I'm going to say is that rather than having U, I will have R multiplied by R0 multiplied by I. Right, so we have here R0 multiplied by I minus R multiplied by S plus minus. This would be equal to LDI dt. Is it correct what I'm putting here?
That's the XY.
That's
I,
right.
I will be divided.
dx or dt?
It's not
That's
going to be
XY.
IR0.
So it will be R0 times I
I2.
minus X, huh?
Yeah,
Yes.
I will.
I minus X.
So we'll have here R0 times I minus R0 times X. So this is the current that goes here, right? Minus R multiplied by X again. Right? You agree with this? My output is still X. Sorry, my output is still. This is what I want. So I'm going to select V again equal to half Lx squared. I'm not sure right now what this will lead, but I can write this is equal to R0 plus R multiplied by X. We take the derivative. So this is LDX dt. Right? So this will be equal to Lx prime multiplied by X. So this will be equal to M multiplied by, not M, X multiplied by I multiplied by X minus R0 plus R multiplied by X again.
X
Square.
X
X squared.
Yes.
But I did not get what I want. So our equation is correct here, L times X plus L dx dt. And we have here R0 because here I still found that output is equal to not input.
The input is I.
Yeah, the input is I, so when I will multiply this one is equal to what? This one is V prime, huh?
Yeah, very good.
So V of capital T minus V of 0. This will be equal to R0, the integral of I times X will be I times Y
Yeah,
minus R0 plus R multiplied by Y squared. So there is, we need to modify it a little bit. Maybe we need to add another capacitance there to see how it works. If we add, if you want to have it based on the output dissipative, but here it should be, there should be some terms that dissipate the energy about R, and it's there only on the output square. So we are able to put, anyway, we are able to put an example where we can show you also how the energy is dissipated at the level of the input. Right? So I don't see it now. All what I see now is the integral of I times Y is equal to V of capital T minus V of 0 minus R0 plus R. Plus R0 plus R squared. So I just changed the coefficient at which the energy is dissipated at the level of the output.
More energy.
More energy dissipation, yes. But I'm not able to see the energy that is dissipated at the level of the input.
Yes.
And this is why I try to change the example a little bit to give
If
you
you
this.
work capacitor, maybe with as voltage source.
But physically, this is what we see. This is what I wanted to show. I wanted to show you that these terms are representative of physical terms that are happening at the level of the output and the level of the output. Unfortunately, I'm sorry about that, the example did not work. So I need to think about another example. I will bring you this example later, inshallah. So these terms, basically, this is what we are telling. They are telling us. They are telling if there is any energy in the system, is energy coming from the supply. There is nothing produced in the system, and this is the definition of passive system. Passive system does not produce energy. And if we'd like to look to where the energy is going, the input energy, we are going to say that the input energy goes to either store or dissipate at the level of the input or the level of the output. There are other terms, sometimes other terms that we can put across between the input and the other states. For example, if there are state variables, we can have internal dissipation of energy based on the states, depends on the state of the system. So, we are not seeing that.
So, I have a question. You're saying there is no energy coming from inside the system.
Yes.
Are not all electrical systems like that?
All mechanical systems.
Electric, not mechanical.
All electrical systems and mechanical systems are like that. The majority they are passive. So passivity is very active in systems that are electrical and systems that are mechanical.
Maybe nuclear plant.
Maybe nuclear is not. Chemical engineer, chemical.
No, that's what I was saying. Because mechanical, when you say a motor, you give it diesel, you can. Do you consider that as energy or not? Because you will transform it into explode.
Repeat this again.
In a diesel motor, you give it fuel.
Yeah.
It will transform it to energy. Do you consider the fuel as energy in the input?
The fuel is the energy.
Oh, so it's not energy.
No. So as usual, mechanical system, as I said, mechanical system, electrical system, they fit very well. Chemical equations, they don't fit the passivity system because you have energy generated from the chemical equations. Yes, chemical reaction.
So you mentioned something about electrical systems. What about in cases of active devices like transistors? Do they still follow the same
Yeah.
rules? Because transistors generally are considered as active devices.
But active devices are different from the passivity that we are looking at here.
Or the concept is different.
The concept is different. Here we are saying we don't have energy. Do you have energy generated by the transistors?
No.
No, but they act as amplifiers.
Yeah, they amplify the system, but they dissipate energy to amplify something.
Yes.
Huh? So if I have, for example, battery in a system and then I'm using it for videos, for example, this battery will dissipate, will give energy to the video devices, the system, but it will lose energy. So there is conservation of energy somewhere.
But then the battery itself, I mean, based on this concept, would be considered as an active device, right?
The battery is the source.
Battery is the source. It's your source of energy. It's your input,
Yeah.
your voltage, yes.
But at the same time, we are storing the energy in it.
Sorry?
So at the same time, we are storing energy in the battery.
I'm really exhausted, so I'm not hearing very well. Repeat this again.
At the same time, we are storing the energy in the battery.
Yes. We are not storing any energy in the battery. Usually the battery is dissipating energy. So you have the battery is decreasing in energy. Unless you have a recharge of the battery at the same time. Recharge is, you have the source is different than the battery. Sorry?
Yeah, because we have another
System with the battery. One system.
Yeah.
Whatever you lose here, you use here. So if we,
Type.
I'm coming again to the storage function.
Yes. If you want to know more about this, you have to take nonlinear course. Anybody took nonlinear course? So if you want to know more about it, this is where you have to go. Yes.
So basically, if we take the function, the b like we will have ln squared. So this is basically depend on how the device store the energy. Like if this is the inductor, then this is current multiplied with the voltage, and we integrate it, then it's like this.
Repeat this again.
Then the storage function will be like this.
Right.
For example, we have inductor, and we multiply the current with the voltage across it, and then we integrate it. Then we'll get the storage function.
No,
in the
but you gave me a good idea here. I'm sorry about this. But we can consider still the input as u, but I is equal to u over I, over R, 0. So if I put here u as my input, and u is equal to I times R0, or u over R0 is equal to R, what will happen?
Let's see. Put u over
To reformulate, changes everything in terms of the words.
It will not change anything?
Because
We have to come, we have to come here.
No, that's the old equation.
Dependent source, not dependent.
It's the old equation.
I mean, if I here input it depends on the states. I equal equation with states, maybe we can show the input.
Maybe. You have to think about it. This is an example.
This is
for you. A homework. You have a question?
Okay, that's I was calculating like this.
Yes.
If
I
this
think
power is equal to I into V, and we have to integrate it to convert it
That's
to
right.
energies, and then we will have the storage function.
That's right. In fact, what usually we should normally have is u, somewhere here u, squared over R0. This is what I'm expecting to have. U squared over R0, and U squared over R0 is the energy dissipated at the level of the unit. But let's say that I encounter, this is why I'm not able to find it. Next time I'll see what it is. But I need to progress with you on this. Huh? So passivity is then a physical property, but it's also a constrained property. You are limiting yourself to certain systems. You are not making it larger. You are constraining your concepts to systems that have this property. Everybody is okay with this? So the rules that we are going to see are for particular systems. It does not mean that other systems cannot be, for example, stable or whatever. But for these systems, we are able to make these conclusions.
Is there any law I can know that I can use this law in this system to know if this system is that kind of system that we're going to use? How I will know? You said that there is a specific system.
These are specific systems. So we are looking to the special condition of passive systems.
Ah.
Okay? So if you have a system H1 and H2, for example, and then you see that there are some properties that are not necessarily respected here, the system could be still stable.
Sufficient but not necessary.
Sufficient but not necessary. Yeah, it's we are just limiting the focus on one particular type of cells. So if you remember, we talked about the small gain theorem, and the small gain theorem talked about gamma 1 and gamma 2, the gain of H1, the gain of H2, and we said that the system is stable if 1 over 1 minus gamma 1, gamma 2 is positive or finite. Now we are looking to theorem 5.1, and 5.1 it says let H1 be strictly output passive and H2 be passive. So we have a system in closed loop. H1 is strict output passive, SOP, and H2 is only passive. If we have this case, then the system is bibostable. Right? So bounded input, bounded output. The system does not have to be linear system. This H1 and H2, these blocks are not transfer functions. They could be nonlinear blocks. But as soon as we are able to write this in this form, even for systems that are transfer functional, you are able to verify that H1 is strictly output passive and H2 is passive, then the system is bibostable. Alright, so this is the proof of this, but we will not go through this. We can go through that later. So we have used MIT and Lyapunov for the feed-forward case, and we are trying to develop it, the understanding of the stability. What we are going to do now is to integrate what we have seen up to now to see how can we say that MIT rule is stable, and how can we change the adaptation rule, right? So this is how the MIT rule works. Basically, we are multiplying y minus ym multiplied by ym multiplied by gamma s. But when we use the Lyapunov, we have y minus ym multiplied by the reference, not multiplied by ym. This is the two difference between the two. So basically what we would like to do is to look to this block diagram and reshape this block diagram, rewrite it again, redraw it again, but we redraw it in this form, H1 and H2. Remember how we did the proof for the feed forward, okay? We had to assume that the system is in steady state, and then ym is in steady state, and then etc. And this gave us only one kind of indication of what will be the condition for the system to be stable. But it was kind of an aseptic analysis. So we would like to see how can we guarantee the stability here for this particular system. So we look to the system and we modify it like this. So we have all this block. This is UC. So if you look at this, you have theta multiplied, this is the feed forward, so theta multiplied by K0, which is the gain for GS. That goes through GS here, generates ym, y minus ym, so the error. So my output here is the error. And then this feedback, the error multiplied by YC, or multiplied by ym, multiplied by gamma over S. This will generate theta. Theta multiplied by K. K here is unknown, so we can put K in gamma if you want, but the general analysis. Then K minus K0 is the error in between the gains, and all this comes back to the system. So all this block becomes for me H2. So we have H1 here and H2 down here. So this is how H2 looks like, right? If we simplify it in the way we did it before. So theta 0 is your kind of the right value of theta. Gamma over S is your other.
H2 here is variable now, because you have UC.
UC is the input. The input there. It's nonlinear. So H2 is nonlinear. H2 here is nonlinear. Changes with UC.
Changes with UC.
And we have seen when we look to the stability condition for the feed forward, UC was in the roots of the characteristic equation. Right? So it depends on the value of UC. So UC is part of the system. So basically what we have to do now, if we would like to show that this system is stable, all what I need to show is that this is output strictly passive. And this one, gamma over S, is a passive system. So this one will be passive, right? We will see a theorem that verifies this for us. So all depends on G. So here what we say, this is the theorem 5.3, it says property of positive real system. So R is a bounded square integrable function. This is your UC. R is your UC. Okay. Right? G1 is the transfer function that you have, which is your adaptation rule. G over 1 over S in our case. Right? Back again, G1 is this block. Right? And this is R. So we have here R multiplied by parenthesis G applied to R again, right? And multiplied by theta. So there is a function here. Right? So if you look at it, you have R multiplied by G multiplied by R multiplied by U again. U in our case is E.
Dr. G here it's G minus G naught over
G here is your 1 over S.
gamma over because the output is error. So
The output is error. So the output is here.
sure it's
This output is U for your system. So in this equation, this is U,
yes.
this is R.
Yeah.
Alright? So for this block, now I'm focusing on this block. Here it says
U is the input, not the output.
U is the error, the input for the block that is
Yeah,
the
the
output.
input for the block, because it's the output.
Yeah, but it's the error coming from the
Yeah, from the.
Both UC and the error is the input to this H1 or H2.
So you have U is here.
Which is the error?
which is here, multiplied by R. So this is the first block.
Result.
So this is R times U. Then it goes through a transfer function. This is the transfer function. Then it's multiplied again by R. So this is the R that we multiplied again. It's clear now? But this is general form for a nonlinear system. This G of P is applied to R times U. Two signals multiplied by each other, but this is a Laplace transform. This is, we talk about multiplication, but it's an operator, right? It's an operator, so we cannot separate R and U and G1 of P. Cannot take R of U out and say this is R squared G1 of U multiplied by U, blah, 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 right? So this is always here, block. This is why we have the parentheses. So this is a signal R times the output of a system where the output of the system is a multiplication between two signals. Make sense? So here the theorem says the following. It says, let R be a bounded square integrable function, and let G1 of S be a transfer function that is positive real. Then the system whose input-output relation is given by this is passive. Right? Everybody is okay with this? There are full proof, of course. There is a proof for this, right? But we are not going to do the proof. So here it means what? It means that I showed that this block, which is H2, is passive based on this theorem. If this one is positive real. Now if I go back, if I show that H2 is passive,
No, we need just to see H1.
if I show that H2 is passive, then I focus on H1. If H1 is strictly output passive, then the system is Bibo stable.
There was a condition on R, which is you see.
Integrable function.
Yeah.
Square integrable function, yes. So this is the condition in R. And the most important part of a theorem is always,
It's G1.
the most important part of a theorem is always, this is my professor a long time ago. He was a genius. He got his diploma in control from École Polytechnique in Paris. And then he worked with the Germans during World War II. Then after that, he ran from Germany, he went to the United States. And in the United States, he worked with NASA to make with them all these kind of missiles and blah, blah, blah. Then his wife, she was working with him, died in the United States, so he was not able to stay there. He left to Canada and he became, unfortunately, a faculty member. He was teaching control. And one thing that he was keeping always telling us is what is the most important part of a theorem. The most important part of a theorem is not the result, or the condition for the theorem. Right? This is the most important part. So here you have to make sure that this is bounded square integrable functions. Square integrable means if you take the energy, integral square, you find it finite. Everybody is okay with this? So if you take this and you change the input u by something that is not finite, it's not integrable, then this theorem does not apply. Everybody is okay with this? So this is a good remark. So basically what we have found now, we have found with all these techniques that we did, so maybe spent 3 or 4 weeks now talking about positive real functions and then how to make sure that it's positive. Then we talked about passivity, and then after talking about passivity, we talked about supply energy and blah blah blah, which is coming from nonlinear analysis. And then we came back to this theorem, and then when to arrive at this theorem is only to show the stability of a feed-forward gain with MIT. Everybody understand what we did here? Clear? All right, so basically the other thing that we found, which is very interesting, is that I can change gamma over S. It does not have to be gamma over S. Right? since the only thing that I need to make sure of is that this is
Passive
stick
output.
output passive, and this one is passive. So I can change this and make it
Whatever.
passive. So one way to change this and make it passive is probably to make it as a PR. Okay? So proportional integral. If I put it at a proportional integral, I will be able to control the speed at which I'm going to make the adaptation. And I'm going also to make sure that theta try to converge to theta 0 as we go on this, right? So here it allows me to explore different adaptation algorithm. Is it clear what I said here? The other thing that I can see is that what will happen if G is not strictly output passive. G, remember G is what?
It will be.
G is your process. Is the process transfer function. So what we can do is that we add another block after E, GC. We call it GC because it's part of our control. So we can add GC such that the most important part is the signal that comes here, U, right, or E. So we can make sure that GGC is strictly output passive. Everybody is okay with this? And then we are able to show still that this MIT rule will work.
So the condition about being output passive is we can like not focus on it. You can just use this GS and
It does not mean that you are able to find always a GS that does this, but this is telling you that you can build your controller, you build all your adaptation rule by looking to passivity. So basically we are trying to what do you call it? Make the system passive, strictly output passive. So ensure that the system is strictly output passive. So basically we are changing the passivity characteristic of the system by adding blocks. So our design is based on passivity. This is why in many papers you will find passivity-based controller. So the controller is based purely on analysis of passivity, right? Or passivization of a system. So the system is there and we got to make it passive in order to use the results of this kind of controller or this kind of development. What I did make sense?
yes.
All right, so this is how we do the compensator design basically for a system. So this is an example, you can go through it very quickly. It just explains that G of S is not strictly output passive. And then we modify GS by saying here, GS has a numerator S plus 3 and a pole at S plus 1. So the numerator comes faster than the poles. So in order to make this system passive, we really changed by GS. We took off the 0 that is in advance,
We make
and
one
put
slower.
then one slower, and we were able to make the system passive. Right. So this kind of a design that, but work on it, do the equations, and you will see how it works in terms of design.
The same GR.
The same PI. See, because PI is strictly output passive.
Yes,
So it's not it's not an issue. All right. There are a lot of analysis like this where we are trying to augment the system. For example, here we have we would like to make sure that the error in steady state is equal to 0 in terms of data and in terms of error. So we modify the equation, we rewrite the equation by decomposing G on G1 and G2. So what is G1 and G2? We look to the system where G can be decomposed like what we did with B minus B plus. We have G2 that G2 is strictly positive, G1 is strictly positive real, and G2 can be anything. Right? So we take a system, we find that we have a system, and we are not able to find GC that will convert it to passive. We take the system, we decompose the two parts. One which is strictly output, strictly positive real or strictly output passive, and the other one can be anything. And then based on that, we are able to identify our augmented error, and then we can go through the same design here terms in order to ensure the stability of the system based on only the value of G2 in terms of adaptation rule. So this is kind of U filter. If you remember last time when we did U filtered in one of the development. So we will stop at this for this kind of systems. The only thing that I would like to mention is here again, as we did before. So this is the algorithm and how to implement the system with output feedback and with the adaptation rule that is coming from MIT rule, either using the augmented error or using the error as it is. But one thing that I would like to mention is this change that we did. We did similar change before when we talked about recursively squared, right? So this change is trying to make sure that the system is less sensitive to the change of phi. Right? When phi goes to infinity, we have this term that will try to keep it down. And then when it goes to 0, there is this term that will try to avoid division by 0. So we just added this.
So what is phi here?
Huh?
What is phi here in this case?
Phi is any of our functions. For example, in our case, phi here was UC, right? So here, for example, UC was our phi. UC multiplied by the errors, right? So we have in this case, whatever function
multiplied by the error.
Exactly.
Okay.
The function multiplied by the error. But epsilon here is not the error only in this algorithm. Epsilon could be the augmented error that we have, and the augmented error is basically looking to the filtered version of UC. Right. So we pass UC through G2. And then we make sure that the epsilon is equal to this. And G1 and G2 are component of G, so we divide G in two parts, where G1 is strictly positive here. And then we keep G2 there. So what else we can talk about this? I think that's it. I'm asking you to read section 5.8 in here. Passivity, I'm not going to give you anything to read about passivity. I will leave this to your nonlinear course. But it's something that is very helpful, even in state space model. So sometimes we design the whole controller based on making sure that the system is passive. This paper is a very interesting paper. I will put it for you in Blackboard. So right now, what we have seen the MIT rule and we have seen the Lyapunov rule only for feed-forward. And we found that they are almost the same, right? It's depending on what signal we are going to use. Either we can call it filtered signal, YM, it's filtered signal required. This paper is interesting in the sense that it takes all the methods of adaptive control and it shows that they are equivalent to each other. Right? So it's just how you are looking at it from which point of view, and that's it. But if you dig more, you will find them all equivalent to each other. So I will put this, and then you can look at it later, inshallah. I think that's it for now, for this. So what we are expected to know, we are talking about positive V and strictly positive V. We have to know this, how to check the passivity of the system and use the passivity theorem. We have to do this. The adaptation gain gamma, and based on the passivity rule, basically it's just to make sure that the system is passive, how to change the system or add G of C to make the system passive, and the application to adaptive control, and the similarity, they are similar. What I would like to do now is design. Right? So we are going to focus not on feed forward, but we are going to focus on adaptive control. Right? And the way we are going to do it is we are going to do it as follows. We start with a method that is not adaptive. So for example, we start with feedback linearization. and then after that we convert feedback realization to adaptive, and we see the difference between the two. Everybody's okay with this? So certain things you have already seen before. For example, feedback realization, I'm pretty sure you have seen it in nonlinear. Backstepping, you have seen it. You have seen also standing mode controller. So these methods you have already seen. But I will again repeat the same method here, maybe different, maybe the same, so I don't want you to be bored. Huh? So we will look at how we design these controllers without adaptive, then how to introduce adaptive in the control, and what will be the pros and cons. Remember the adaptive, you are not supposed to jump to adaptive control every time you would like to do controller, unless the control requires you to do adaptive. Then you do adaptive. Otherwise, you keep yourself not away, because adaptive, it allows you to use the maximum performance of a system, but it's a little bit more complex than the other type of designs. Anybody has a question about what I was saying here? طيب, I will stop here. Wednesday there is the graduation, so I don't want you to be trapped in the traffic during.
When I was there.
So